So this is part 2 of our 9-5 notes. 9-5 notes are complex numbers and DeMoivre's theorem. So we've spent some time looking at complex numbers and changing them to polar, and then changing polar back to complex numbers, rectangular complex numbers. And now we're going to look at DeMoivre's theorem. So DeMoivre's theorem is if I've got this complex number in its polar form, right? Our polar forms are r cis theta. Then if I want to raise that complex number to a power, I take my r and I raise it to that power, and I multiply the angle times the power. So I'm going to use an exponent here and then multiplication for my angle. So it gives us a really slick, easy way to take something and raise it to an exponent. So we're going to look at that for example 6. So in example 6, I want to raise 3 plus 3 square roots of 3i, all raised to the 4th power. And I could use Pascal's triangle. I mean, I know how to expand binomials, but we're going to try using this polar form using DeMoivre's theorem instead. So what I'm going to do is I'm first going to change it to polar. So that's going to be our first step because DeMoivre's works when we're in polar. So first is going to be changed to polar. And then we're going to use DeMoivre's. And then we're going to change back to rectangle complex. And we will play around in class with just raising things using Pascal's triangle to the 4th power versus using DeMoivre's, and just kind of comparing our work steps and what's going on. So if I want to change this to polar, I need to draw a picture. This is going to be in quadrant 1. We have 3, and then we have 3 square roots of 3. So I'm thinking about how this is kind of a familiar triangle. This is like a 3 times 1, 3 times square root of 3. So I could think about how I have those triangles that are 1, square root of 3, 2, a 30, 60, 90 triangle, and how I can add basically an x to each of these. I can multiply them all by the same thing, and I can keep getting special triangles. And this would be with 60 across from that square root of 3. Or pi over 3, right? We're going to use radians on this. So I know that my third side is going to be 3 times 2, and that this angle inside is going to be pi over 3, or 60 degrees. So then right away, I have the polar form. My radius is 6, and my theta is pi over 3. And so I can write 6 cis pi over 3, and then this is all raised to the 4th power. So I changed to polar. Now I'm going to use DeMoivre's. So DeMoivre's says I can take 6 and raise that to the 4th power. So I've got an exponent and then cis, and then I'm going to take my angle and multiply by 4. So 4 times pi over 3 would just be 4 pi over 3. 6 to the 4th power is, and my work just disappeared, 6 to the 4th power on my calculator is 1296. And so I've done it. I've raised it to the 4th power, but now I want to change it back to rectangular. So to change it back to rectangular, I need to just evaluate now. So remember, this is 1296 times the cosine of 4 pi over 3. And you don't have to write this step out. And then we'd have a plus 1296 times the sine of 4 pi over 3 times I. So we're changing back to rectangular now. So 4 pi over 3, let's go ahead and graph that. That's going to be pi over 3 past that line, because 3 pi over 3 would be 180, and then 4 pi over 3 would be adding 1 more pi over 3 to that. And then I'm going to label negative square root of 3, negative 1, 2. And now I'm just going to take the sine and cosine. So my cosine of 4 pi over 3 would be a negative 1/2. So 1296 times a negative 1/2 plus 1296 times the sine is the negative square root of 3 over 2, and then this is times I. And now all I have to do is simplify. So this is going to be negative 648 minus 648 square roots of 3i. So definitely, I think, more straightforward even than using Pascal's triangle and having to multiply all that out, especially with a square root. So our last problem, we are finding the fifth roots of -2 minus 2i. And if there's fifth roots, I want to just point out that this means that there are going to be 5 answers. So when there's square roots, there's 2 answers. It's kind of weird with I. The really cool part, though, is we really can take our answers, raise them to the 5th power, and get back to this thing. So if the 5th root of a number, of a complex number, is -2 minus 2i, then that means if I take that complex number and I raise it to the 5th power, I have -2 minus 2i. So if my 5th root is equal to -2 minus 2i, that means if I raise it to the 5th power, I get the -2 minus 2i. So we're going to be using DeMoivre's on this. And so I am going to take that right-hand side and I'm going to have to change it to polar. And then I know that z is a complex number, and so I'm going to write it as r cis theta. And if that's being raised to the 5th power, this gives me a chance to use DeMoivre's. And I need to point out that this is completely different than what the textbook does. They have these crazy formulas for this stuff. I think the way that we're going to solve using DeMoivre's is going to kind of link back to things that we learned for solving in earlier chapters. And the work is actually much more straightforward, a lot less letters. So -2 and -2. So let's go ahead and graph that. Oh, 2 sides are the same. That means I've got a 45-degree angle in here. And we are going to use degrees on this because it's more intuitive. And so let's see, the third side would just be 2 square roots of 2. So I have my r now. My r is 2 square roots of 2. But my angle isn't just 45, is it? My angle is going to be 180 plus 45, or 225. So that's going to be my theta. Okay, so on the opposite side now, I have 2 square roots of 2 cis 225 degrees. So now I'm going to use DeMoivre's. That means that this is r to the 5th cis 5 theta equals 2 square roots of 2 cis 225 degrees. And now this reminds me of so many other problems that we've been doing in math where it's like, here's the r parts, those have to match up. Here's the angle parts, those have to match up. So we can write 2 different equations from this. So r to the 5th is going to equal 2 square roots of 2. And then, and 2 square roots of 2 you might recognize is just really the square root of 8, right? I could write this as 2 squared and put it inside. And so 2 squared times 2 would give me 8. So this is the square root of 8. And then to get rid of a 5th root, I would take both sides and raise them to a 1/5 power. And let's see. So this is like 8 to the 1/2 to the 1/5. And really, we could put it in a calculator here, but I'm just saying that this is 8 to the 1/2 power to the 1/5. So it's really 8 to the 1/10 power. And that's going to be, we want to use a lot of decimal places on this, 1.23114. So now I'm going to do the angle part. So 5 theta is going to equal 225 degrees. But just like before, I have to remember that every time I go around the circle, we get answers that work, basically. So I'm going to write plus multiples of 360. And our answers are all going to be between, our angles are going to be between 0 and 360. And let's put degrees on those. So now I'm going to divide by 5. So theta is going to equal, let's see, 225 divided by 5 is 45 degrees, plus, and instead of multiples of 360, we're going to have multiples of 72 degrees. So that means my first angle is going to be 45. And this is kind of like that n times theta thing. So then my next one would be 72 plus 45. That's 117. And then I would add another 72, and I would get 189. And then I would add another 72, and I would get 261. And then add one more, and I get 333. So you can see I can't add another 72 without getting to 360. And so this is going to be the angles for our 5 roots. So we have R, and we have all of our different 5 thetas. And so we'll put those together. I have 1.23114 cis 45, 1.23114 cis 117, 1.23114 cis 189. So we have to do all 5 of these, and we're going to have to change them back to rectangular. So sometimes we'll ask you to change them back, sometimes we'll not, but in this case, we're going to practice that. So remember, when I'm changing it back to rectangular, all I'm doing is the cosine of 45 and the sine of 45. So like on this first one, 1 square root of 2, here's my 45. So I would be doing the cosine and sine of this. Because we have so many decimals already, we're not going to worry about keeping this a square root of 2 over 2 and simplifying. We're just going to go straight decimals. So if I do this times the cosine of 45 plus this times my sine of 45, I'm not going to write it all out here. Maybe I'll write it all out on just the first one. So remember, this is what we're doing. Cosine 45 plus 1.23114 sine 45 degrees. So on this first one, I would get 0.87 plus 0.87i. So this is one of my answers. So if I raise that to the 5th power, I would get back with -2 minus 2i. My next one, 1.2311 cis 117. So 117 would be over here. And when I plug this into a calculator, I get -0.56 plus 1.10i. And then I need to do 189, so that's going to be just passed over here. -1.22 minus 0.19i. So I always like to kind of look at my signs. Because I'm in quadrant 3, I know that both the x and the y parts should be negative. So that's matching. 261, so in quadrant 3 again. And this one is -0.19 minus 1.22i. And then my last one, 333. So this is going to be 1.10 minus 0.56i. So one thing I really want to point out here is I left so many different decimal places for r, so that in the end I could just round it to 2 and it would be pretty accurate. And I do have my 5 roots. So all 5 of these, if I take them and I raise them to the 5th power, I would get back the -2 minus 2i. So that might be something that you just try to do on your own just for practice. And maybe you just use the polar form because that's easier. You can use DeMoivre's. This is the end of our 9-5 notes. It's the end of part 2.